What's going on, guys? Welcome back to this video. Today's video will be on HackTheBox, and we're going to carry over the intro to binary exploitation track. So today's machine or today's challenge will be Pwnshop. So Pwnshop is similar to HTB console in that we will use the same buffer overflow technique to get the final flag, which is Ret2libc. But we might do additional things on top of what we have done on HTB console by doing some stack pivoting, and we will introduce other new concepts because this challenge is kind of similar to HTB console, but it has a couple differences. Okay, so this is a challenge. We download the files, and as you can see, guys, we turn on the instance because we're going to interact with the binary later on. So we start the journey by first we want to identify the nature of the file, so we issue the command file Pwnshop. As you can see, it's 64-bit executable file and it is stripped. We already explained, guys, what all that means. Okay, so we're not gonna again repeat again and again. Now we check the protections. We have NX enabled, means the stack cannot be executed or cannot contain code execution, and we have Py enabled. So I mentioned in my notes, guys, about these protections. So as you can see here, we have NX is a kind of protection where executing code in the stack is prohibited. Now position independent executable, and that is what is enabled here. So the binary and all of its dependencies are loaded into random locations within the virtual memory each time the application is executed. So it means the addresses in memory are loaded every time with different values when the application starts. This makes the exploitation a bit more difficult, but if we are able to leak a couple addresses in the binary and use them to find system address, SH address, and build the proper rope chain and gadgets by using the gadgets, we will be able to bypass this as well. Now let's take a look at the binary using Ghidra. Okay, so that's the first function, which is the by function. Now, mind you, guys, let's first simulate how the binary works. So we're gonna go to desktop and then Pwnshop. As you can see, we have three functions: buy, sell, and exit. If we type buy for buy, sorry, we aren't selling right now, but you can place a request, enter details, anything, and then it gets you back to the main menu, which leaves us with the sell. So if you take a look at the buy, so we have a variable defined with 72 bytes, allocated with 72 bytes, and then the application reads more than 72 bytes. As you can see, this is around 80 bytes or 82 bytes into the variable. Now the variable is only 72 bytes. Okay, so basically here the buffer overflow vulnerability lies exactly here. We are reading an input from the user that exceeds the allocated size of the buffer. So let's put that in mind. Also take a note of the function buy. It has the offset or the address at 13.2a. We're gonna need this. That's why I'm telling you guys to take a note of this address, 13.2a. Okay. All right. Now let's go to the sell function. I believe the sell function is somewhere here. Okay, this is the selling function. As you can see, we have variable declarations, and then we have this local 20 underscore 20, and this is a memory address. So this is kind of a memory leak. Okay, let's put that in mind as well as a note. Take it as a note, and then we have the prompt. What do you wish to sell? And that's what we get here. What do you want to do? So if we type 2, run that again, 2. So what do you wish to sell? So we are here, and scrolling down, we read the user input using the read function. Remember that the read function doesn't add the null byte to the end of the string. So this opens the chances of leaking binary addresses, especially if the read function was used with the %s. %s indicates that we are reading a string from the user. So take a look at this one. So read, and then we store the input of the user in the variable autostack 48. So exactly we take 8 bytes. And then we ask the user how much do you want for it, and then again we use the read to read 8 bytes and store it at local 28. So say if we don't go exactly as the program flow or as the program wants, we're going to end up with else here. So else is going to say what the best I can do is $13.37. Look at this. This is the string because it expects a string from the user, and then remember that we use the read function. It means if we use the %s and read at the same time, it means that the program will expect a null byte, but there will be no null byte, and thus we'll be able to leak memory addresses. So that is demonstrated by this. So if we go back, what do you wish to sell? Let's say test. And how much do you want for it? Let's say 1, 2, 3, 4, 5, 6, 7, 8 bytes exactly. Take a look at this. These are unrecognizable strings. Now these are the leaked. This is supposed to be a leaked binary address. Supposed to be a leaked binary address because, as I said earlier, guys, when there is a use of %s, okay, with the read function to take the user input, here if there is no null byte added by the developer, there will be no null byte added by the program code because the read function doesn't add null terminator. Not adding null terminator will leak memory addresses. Now this is actually leaked here by the unrecognizable strings here. Now if you are able to craft a Python code and encode these into hex, most probably we're going to end up with a binary address. Okay, so the first part of the exploit code is where we actually catch the leaked memory address. So as you can see here, we enter, for example, 8 bytes for the sell function, and then we use receive until after the question mark. We catch everything that comes after the question mark and encoded it to hex. This will reveal the leaked address. So after we leaked an address from the binary, guys, we're going to need to calculate the base address. Remember that the binary has spy enabled, so we're going to need to leak a base address from the binary. To do that, we're going to use the leaked address here, okay, and start GDB debugger. So we start GDB here, and I'm using the GIF plugin. For more information on how to install the GIF plugin, I have outlined that in my notes. So we use wget, and then we put the startup at the GDB initialization. So with GIF, guys, I'm going to scroll down to a point where I printed the memory mapping. So we need the memory mapping because we're going to need an offset that will be used to calculate the base address. Okay, that offset, how can we calculate that offset? We're going to first subtract the start of the memory here from any address on the binary. So let me scroll up, guys, and show you. Scrolling up, let's see. So here what I did, I simulated a test. So I selected 2 to sell, and what do you wish to sell? I just use test, and then I exit the process. Scrolling down, Here I use grep test. I want to see where in memory my input has been directed to. So as you can see, this is with \n, and we have this address. So that's where the test is. So I printed the contents of this address. Okay. And here we can pick up any address, guys. So this one here can be used as a start. So we take this address that represents the start of the input, okay, that we have sent to the program, and then we subtract it from this address. How we're going to do that? We're going to say px, and then we're going to go back. Yeah, it's here actually. Look, I did it before. So we subtract the address, the start of the input we send to the program, minus the start here of the memory, and then we got an offset. Now this offset will be used to calculate the base address. Let's go back to the code. So ELF address, which is the base address, we subtract the address that we just leaked here minus the offset we have just calculated, and then we end up with the base address. So this is the leaked address, and this is the base address. Now after we have leaked the base address, we can say that we successfully bypassed the portable independent executable, but the position independent executable. I don't know why I said portable. And then we can start crafting the rope chain. To craft the rope chain, guys, we need to use gadgets. Now how many gadgets? That depends on the space in the memory. So reminding you guys that rope chains are, so gadgets are sets of instructions that end in return. Every gadget has an address which we can add on the stack, so that when a gadget is executed, it returns to the stack. That's the gist of bypassing binary protections, namely NX. So instead of executing code on the stack, we let the gadgets execute, and that's too many gadgets next to each other will form the rope chain. So now we need to do what? We need to create the rope chain. So first, to create the rope chain, guys, we have to create, or we have to calculate or find the gadgets, all the relevant gadgets. So to find the gadgets, we're going to use rope gadget. Exactly. Now the binary this time will be Pwnshop. Now although we can override the return address and redirect the program execution, we need to make sure that we have enough space for the gadgets. Okay, so for that reason we're going to grep RSP, and let's take a look. So we have this. It subtract 28 bytes from the RSP and then return. This will make sure, guys, that we have enough space when we subtract 28 bytes, because a gadget can be 8 bytes and above. So if you have 28 bytes, it means we have enough space for the gadgets to execute on the stack. So here, this is the offset, the first offset here. We're going to need to take a note of this gadget. The offset is 1218, and as you can see here, guys, in my code, that's the first offset. Okay, it is 1219 found from here. That's the first gadget. And as you can see, guys, we add them to the base address. So for every gadget we find, we add it to the base address that we just calculated. Now the next thing we need the pop RDI. Now pop RDI here is typically needed in every case of crafting a rope chain. As you can see here, I put that in my notes, so we're gonna need to go back and find the offset of the pop RDI. So here we don't have pop RDI. Let's print all the available gadgets and find the pop RDI. So we have this one, 13th C3. So we found the pop RDI. Now the other offsets we need to find is the PLT and the code. So how are we going to find these? We're going to again use the rope gadget. Now instead of looking for the pop RDI, you can simply type rope gadget and then grab it. Hopefully maybe this will work. RDI. Let's see. Yes, it worked. Alright, now we need to find the offsets of GOAT and PLT. Now remember the by address I told you earlier, guys. We need the offset of this address as well, because that's where the buffer overflow lies. So this address or this function is the by function. This is the offset 13 to A. Going back, we have it here. Now the rest is the PLT, puts PLT, and the setvbuf. So we're gonna go back and grab these from the disassembly of the function. We can print a quick disassembly of the function or the binary using OPG or object dump. So and then the m for Intel -r, the binary is Pwnshop. We're gonna grab setvbuf. Okay, so this is the offset, and also we're gonna need for the PLT, so we're gonna need to grep for put at PLT. Here it is T, not R. Okay, so we have these offsets. It is 1 or it is 10, 30. So now we have all of them here. After we calculate all of the needed offsets, guys, we can now craft the final payload. But there is one thing left, which is the system, and remember that we need the binsh and system as well to execute a remote code, or to have a shell when we execute the binary offset. Because remember, when there is position independent executable with NX, we need also to bypass ACLR. How to find these addresses? I've also guys these addresses. I've also guys outlined how to find these in my document, but I'm gonna do that again here. So we're gonna open a new tab, and let's see where is the command to find the system offset. Read elf. Now to do that, we're gonna just need to copy the commands. So finding first the libc system function, we can either execute this or this. Let's take this one. Find the offsets of the system. Now note that, guys, this is local, meaning this is relevant to my machine, not on the HackTheBox machine here, which is Pwnshop. So later on we're gonna need to change these values, but first I have to understand the methodology and how to find them. So first we find them locally. That's the system, and for we're gonna need also for, I guess, binsh. So binsh. Nope. Let's go back and see the relevant command. Oh, we need the strings. So let's take this one. So with strings we can find the binsh offset, and we're gonna need also the setvbuf, this one. So this is the offset here. Going back, we update the values. Now I put these values in a comment because we're not gonna use them. I'm just showing you guys how to find them in case you are doing a buffer overflow attack locally on a target machine directly. Here these values are relevant to my machine. Now these are the correct values. They can be found online depending on the architecture of the target machine. That's why we have this website here. In this website we can find the relevant offsets. Let's say we put set the buffer and the address, it is A80 E80, and then we find, so we have these. Let's go with AMD 64. I guess it is the one relevant to the machine. Open a new link. Okay. Alright, so as you can see, for every architecture we have the offsets for system, for the buffer, for BNSH. Replace them with the local value. So replace the local values with the values you found online. Now the last thing we want is the glibc address. It can be found by subtracting the address we found earlier for the buffer minus its offset, and therefore we add all the addresses into the final payload and then we execute. Let's see how it goes. The IP and the port, as you can see, are defined, and then we execute. So we got a shell ls, and there you go guys, this is the flag for this challenge. So guys, that was it, and I will see you in the next video.